Okay, so our project is electromagnetic and ultrasonic flow meters. My name is Kirk. I have Alex and Jacob with me, and let's just dive right into it. So we're going to be talking about electromagnetic flow meters and ultrasonic flow meters. We'll be talking about what it is, the parts, how they work, Faraday's law explanation, the Doppler effect, and real-world applications of both of these. So starting out, we'll just go over some basic definitions. A magnetic flow meter, also known as a mag flow meter, is a volumetric flow meter that has no moving parts. It's ideal for wastewater applications or any liquid that is considered conductive. Mag flow meters are ideal for low pressure and require little to no maintenance. Mag flow meters will not work with hydrocarbons, distilled water, and non-aqueous solutions. Next, we have ultrasonic flow meters, also known as the non-intrusive Doppler flow meters. A volumetric flow meter which requires particles or bubbles in the path of flow. Ultrasonic flow meters are ideal for wastewater applications or any conductive liquid. UFMs can work with clean water but require aerations. They are ideal for applications with low pressure, chemical compatibility, and low maintenance. And lastly, the Doppler effect, which is related to ultrasonic flow meters. This uses a reflective ultrasonic sound to measure the fluid velocity. The frequency shift between the ultrasonic frequency, the receiver, and the fluid carrier gives the relative motion.
Now we're going to start breaking down the individual main topics. We're going to get into electromagnetic flow meters first, and this is the parts and how they work. First, we got to have a pipe with a liquid flowing through it. The liquid's got to be conductive or water-based, and then to actually get the magnetic field, we need the coils. And then the electrodes that will float in there and send the signals to the sensor head through the liquid, which then determines what the flow velocity is, and based off Faraday's law, which we'll get to here in a minute. Okay, as you can see here is our electromagnetic flow meter. On top we have our transmitter, and on bottom is our sensor. The sensor will take a measurement of the flow using an induced voltage, which it'll generate through the electrodes. The transmitter converts that voltage into a flow measurement and then sends it to a control system. As you can see here, you can see our coils right there wrapped around, and then our electrodes on the outside. This will generate a magnetic field when the transmitter generates a current going through the coils. As the pipe begins to fill up, or is full, it'll start to separate the negative and positive ions to the electrodes in the magnetic field. This will generate a induced voltage and then be sent to the transmitter. Specifically, the liquid needs to be conductive. Therefore, if it's not, this won't work. This will bring us into Faraday's law. There's 5 different variables in this. E being our voltage, K being the constant, B is our magnetic field, and D is the distance, and then V would be the velocity. With these, we can then calculate the induced voltage, which is hand in hand equal to the flow. So as the sensor gets the flow, it'll send it up to the transmitter, and then the transmitter will then spread it into a conversion. So that's how they work. Faraday's law, which is E being the voltage generated by the conductor, K a constant, just relative to any equation, V velocity at the conductor, and then B is the magnetic field strength, and D would be the length of the conductor. There's many applications to this. Mainly we do wastewater. Mainly it works best with wastewater, but there's also, you can work with chemicals, food and beverage, power, pulp and paper, mining, and pharmaceuticals.
Alright, and then for the other half here, ultrasonic flow meters, we have the liquid itself, which requires a certain percentage of particles or bubbles or conductivity. We have the transducers, which send and receive the sound wave signals, which you can see in both the pictures we have on the side here. The upper picture is a single sensor ultrasonic flow meter. The lower picture is a setup using two sets of sensors that each send and receive signals rather than bouncing off of the pipe. And then we have the transmitter, which would be like the brain or ECU, if you like cars, of the ultrasonic flow meter. That's where those signals are processed in order to determine the flow rates. Back to the bubbles and the particulates. Aeration. It's required to have at least 100 parts per million of at least 100 micron particles. So it's just a certain size of aeration. It's a value of bubbles. And then ultrasonic clamp-on meters are essentially in effect in the industry, as their accuracy is greatly reduced. Most of the flow meters that we've looked at, ultrasonic and mag flow, tend to get within 5% accuracy. So the ultrasonic clamp-ons having a plus or minus value of 20 is quite significant. Alright, so as you can see here, we have an ultrasonic flow meter with the transmitters and receivers set up. They're placed opposite of each other at a 45-degree angle. The ultrasonic sound waves are alternatively sent due to the piezo electrical effect, which facilitates the conversion of mechanical energy to electrical energy utilizing a crystal. When the waves travel with the flow upstream, they're going faster than when they travel against the flow downstream. As the flow increases, the velocity increases, causing a greater difference in the frequency shift. And the frequency shift is the time between the signal being sent, as you can see here with the little blue particle and red particle. And then the governing principle behind an ultrasonic flow meter is the Doppler effect. So the Doppler effect is what is utilized by the transmitter, the flow meter's brain, to calculate the fluid's velocity. So sound waves are sent and received typically at a 45-degree angle between either the single or dual transceivers, transponders, transducers, and then frequency shift between sound waves traveling upstream and downstream is proportional to the velocity of the fluid. So an explanation of that is over here on the right, where T is the transit time, or the measured time between the signals being sent and received. D is the distance between the transducers, and then underneath that we have the velocity of the sound or the signal being sent, and then U is the velocity of the flow or fluid. So then given those bits of information, plug them in, solve it. As far as applications go, it's more common in oil or gas applications, oil and or gas applications. You'll see that some of the other less common uses are similar between the two. Like we have chemical, food and beverage, pulp and paper, it's shared between the two. A couple differences: it's good for corrosive, because the ultrasonic relies more on the particulates in the fluid, so using a corrosive or chemical fluid, something that isn't distilled or clear, tends to be more applicable.
I believe that's all we have, guys. So hopefully you liked our presentation, and thanks for listening. Any questions?